Okay, we have work to do. And I guess on Tuesday we finished, well, we started the 3 Solomon codes. We barely understood how to encode using them. Who of you was in the exercise class on Wednesday? So there you practiced, I guess, these finite fields. It's arithmetic modulo Q, that is primitive generators, all these things, polynomial divisions. I hope that's okay now. If not, you can always go back to this practice problem set where I think those things should be explained. But that's sort of the foundations. I guess Blake did some exercise where you also encoded some things. So I hope this makes sense. Decoding with Solomon codes. So today we have to mostly talk about decoding, but I want to just remind you of the setup. And I think I was imprecise in one spot, so I want to be more precise today. So the alphabet was FQ, let's say A. It's FQ, where Q is some prime. In retrospect, the prime should have been called P. But Q it is. Then there's a bunch of parameters that you get to choose. Parameters. And so there's K, right? That's the number of symbols that we want to encode. N is the block size. And then there's also Q, and I think last time I wrote less or equal to, but I think for some of the properties we need today, we actually want this to be strictly less for the construction I'm sketching. So I'm sketching a certain kind of construction of Reed-Solomon codes. Sometimes they're also called BCH codes. And I think this should be a better provision. I mean, last time we did not assume this, and so things were so fine, but if we go back and you ask, can I correct, like we had this example with Q equals 3, I think, and a 1 and 3, like 1, this was 1, 3, 3. And then the encoding was something like minus S, 0S, of like a bit less, maybe you remember this. Okay, so S and F3 was encoded instead of this triple. But now, of course, if I erase those two guys, then it's always 0, like no information is left about what you put in. And that, I guess, comes from the fact that here actually N was equal to Q. Okay, so that's why I want this as equal. But it's not as important because I want to focus on the algorithms anyway. But if one goes to the math and one tries to really prove these things, this will come out. So these are parameters, and then we had this thing called a generator, or more precisely, primitive element of FQ. So this was a number such that when you keep multiplying it with itself, you get all non-zero numbers in FQ. All zero numbers modulo Q. And then the claim was that whatever the code construction was, it can correct up to well, exactly the difference between N and K many erasures. Or up to T over 2 errors where you don't know the location. So who remembers what an erasure was? Well, I guess I almost said it, right? An erasure is an error whose location you know. So you could imagine, like you, I don't know, like you have your QR code and someone, makes a hole in it, right? And then you know where the information is missing. So that's an erasure code. So that's a practical thing as well. And but something like a random bit flip, and it's just something flips, but you don't know where. That's more like a general error. And so erasures are more special. Erasures doesn't mean that somehow your bit string is shorter. It just means you know where the error happened. Okay, you can grab so that many erasures, erasure errors, or up to T over 2 rounded down arbitrary errors. So errors at unknown location. At unknown location. All right. And one ingredient to the construction was the so-called generator polynomial. That for all purposes is just the following thing. General polynomial G, and that's just the product of x minus alpha squared, and so on, up to x minus alpha to the t. So t is the same number n minus k, so it's the redundancy of our code. And so this is the polynomial with zeros alpha squared, and so on up to alpha to the t. Okay, so maybe this is our t, same t, and alpha is the thing from here. Okay. So we fixed this, we know this generator polynomial, and then the encoder was very simple. Let's put it in a box. So the input to the encoding algorithm, encoding procedure, is, well, it's a string that we want to encode. A string over our alphabet A. So S K and A to the K. Okay. And so what we're going to do is we're going to interpret these K coefficient of all these k symbols, these k numbers modulo q, as the coefficients of a polynomial. And so the polynomial should have degree k minus 1 because we have k numbers. So that's called the polynomial p. So this is s1 plus s2 times x plus s k x to the k minus 1. And it would have been so nice to start indexing with 0. These things would have lined up much more nicely, right? That s0 would be the constant part, s1 would stand in front of x to the 1. Sadly, our book is indexing starting from. Okay, so that's a polynomial of this desired degree k minus 1. And now we want to sort of add this redundancy. So one way of adding redundancy is just multiplying by x to the t. And then sort of what this means is just, right, if I multiply this polynomial by x to the t, then s1 gets an x to the t, s2 gets an x to the t plus 1, and so on up to the end is x to the t plus k minus 1. But t plus k is n. So we get a polynomial. I mean, it has a bunch of zeros at the front, right? But it's a polynomial that has n coefficients. But now somehow we haven't built in redundancy in an interesting way because we just added zeros. That's no good. So we somehow want to do something non-trivial. So what we do is we want to somehow boost this polynomial and modify it such that it's a multiple of g. Was there a question?
Yeah, sorry, I was asking what x exactly.
Oh, what x is?
Yeah.
Yeah. So these are polynomials. So that's just the unknown. That's the variable.
Okay.
So these are, think of them as functions, and x is the variable. So maybe I could write p of x or something. Okay. And then we'll plug in numbers into for x.
Okay.
So you write something like p of 3, and then that's, we substitute 3 for x, and then all arithmetic will be modulo q. So also all these coefficients, we only have to worry about modulo q. Thanks. Okay, so we have this guy. So now what I was saying is we take this polynomial, we multiply it by x to the t. Now we have a degree n minus 1 polynomial. That just has, like its coefficients are 0, 0, 0, and then s1 up to sk. Now I want to massage those first t coefficients, the one that I just sort of initialized with 0 when I did this multiplication. And I want to modify them such that this polynomial becomes a multiple of g, of our generator polynomial. And the way to do it is to do polynomial division. So I will just divide this polynomial by g, then there will be a quotient and a remainder. I'm going to remove the remainder, and then the resulting object will be a multiple of g. Okay, so that's something I discussed. I put on this practice set. Okay, whenever you have two polynomials, a and b, b should be a non-zero polynomial. Then you can always write a as q times b plus r. The r is the degree of r is less than the degree of b. Okay, and this thing you would call the quotient. That's what you would call the remainder. If I remove the remainder, if I subtract the remainder from a, then I'm left with something that's a multiple of b, right? And so we're going to do exactly this, where a is this polynomial p times x to the t. B is our generator polynomial. Okay. So let's give this thing a name. So the remainder usually we denote by something like a mod b, right? So that's usually the remainder. Similarly for integers, right? If I run 11 modulo 4, it's the remainder for integer division 11 divided by 4. Okay, so same thing here for polynomials. So we take this guy modulo g. We call this the remainder r, just like over here. And so now I can fix p. I can replace p by p minus r. And now this object is a multiple, right? So I'm literally doing this. So this thing is p times x to the t. This guy is g, right? I said p times x to the t mod g. That's this remainder. I subtract the remainder from p to x to the t. I get a multiple of g. Okay. I guess a less complicated way would be to say, I don't know, let p be the quotient of this by this. But I guess you would actually calculate it in this fashion. And then the algorithm was on the practice side. Okay. So the key was, well, this guy has a degree n minus 1. Now the degree doesn't change, right? I'm just subtracting this thing, which has lower degree, which has degree at most g. Degree of g is, where is it, t? So somehow what we're doing is we're taking this polynomial, right? So this polynomial p times x to the t. If you think of it, it's like 0 plus 0 times x plus plus 0 times x to the t minus 1. And then, right, because we multiplied by x to the t, there's like s1 times x to the t, and so on. So now I can smoothness, plus s k times x to the t plus k minus 1, which is x to the n minus 1, right? That is this polynomial. And now this remainder, right, is just going to modify these zeros into something else, into something smart. But it's going to leave these s's invariant. So our code is what is sometimes called systematic for weird reasons. A systematic code is one where somehow the message you're encoding is part of the code word. It's just the last k coefficients. Okay. So after subtracting r, we're going to change these guys, and the resulting object is called m. Okay. And then what is our code word? Our code word xn is exactly the coefficients of m. Okay. Because m has degree n minus 1. This is again it's obtained by taking this guy modifying here up to t minus 1. We can store it by taking all these coefficients. Okay. And we take them in the same order as before. So x1 is this constant part, x2 is the linear part, and so on and so forth. Okay. So that's our encoding. Are there any questions about how this works? Okay. And so that, yeah, indeed, the things to remember, maybe we can write down these properties here. Xn has this form, right? The code word, and I'll write some of the tuples explicitly, like as a list, because now it's like if we have like not bit strings but kit strings, then it's like weird. I'm writing things like 1, 2, and you don't know if it's 12 or 1 and 2. So I'm writing this as a list. So x1, x2, and so on. So as you were saying, the first t coefficients can be different, but then follows s1 always, s1 up to sk. Okay. So these things we don't know. There's our parity bits or our checksums or whatever. So these are new, but the s's are really just the source symbols. S1 up to sk. It's like it's literally the message was okay. Come on a second. That's one fact, and the other is, again, as we discussed, m is a multiple because we remove the remainder. It's a multiple of the generated polynomial g. And because the generated polynomial has these nice zeros at alpha, alpha squared, and so on, we now know that m of alpha is also 0, m of alpha squared is also 0, and so on up to m of alpha to the t. Okay. So these are t conditions that we can check when we receive a code word, and if any of them is not satisfied, then surely an error must have happened, and we can try to fix the error. Okay. So that's going to be the plan. If I find my nice yellow charcoals here. Very good. Maybe we want to have a running example. Let's see if I can put this here. Move it up. I have changed my example now so that q is indeed larger than n. So my example looks as follows. I'm going to encode again a single symbol into 3 symbols, but I'm choosing q to be 5. Okay, nice try. And my generator, I still choose to be 2. Last time we checked that 2 is also a good generator of f5. Okay, so this is now 5. Okay. So that means that t, sort of our redundancy, t is 2, 3 minus. So we're adding 2 extra symbols, pentads or something, I don't know. And our generated polynomial, what's our generated polynomial? Well, it's x minus 2 times x minus 4, right? Because that's 2 squared. Now, because I'm working modulo 5, minus 4 is the same as plus 1. I like smaller numbers, so I'll write plus 1. And now maybe we can just multiply this out for completeness. So we get x squared minus 2x plus x minus x minus 2. Okay. So that is our generated polynomial. And so now if I encode a message, let's say s in f5, then it's sort of not hard to check. What should it be? So in general, one has to do a calculation, but here we don't because we know that this message will be a multiple of the generated polynomial. somehow the generated polynomial has degree 2, so it already has degree 3 minus 1. So the only thing, like it has to be a scalar multiple. So it actually has to be s times g in this case. So if you're encoding a single symbol, things are somewhat simpler. So you could either calculate it or you could sort of plausibly believe that this thing is just a coefficient of s times g. And I guess we put the coefficients in this order from constant to linear to quadratic term. So this should be minus 2s. Let me just check. Yes, minus 2s. Right. Then minus s, and then s. Let me pull this up. Again, this is the case because we know that our message polynomial m should have degree n minus 1, so it should have degree 2, and it should always be a multiple of the generated polynomial, but the generated polynomial also has degree 2. So we're looking for a multiple of the generated polynomial that has the same degree, so it must be a multiple by some scalar, by some number. But we also know that this last coefficient has to be s, because we know the last one never changes. Right? The last k ones never change. Here k is 1, so the last one should never change. And so from this we can infer the general story. Again, this is sort of a shortcut, and I probably spent more time justifying it than just doing the calculation. But maybe it's fun for you to do the calculation. So that's our running examples now. Any questions about at least what I wrote and the claims I make? So one thing, right? As our source message gets encoded into 3 symbols. And actually, this, right, just to be clear, this is not just a bit. It's like 1 out of 5 possible messages, and each of these letters can be 1 out of 5 options. So 125 code words. Cool. So how do we decode? How to decode? Has anyone thought about this? Right. So when we decode, we imagine. So suppose we imagine receiving some channel output of some arbitrary channel. Let's call the output y to the n. So it has the same length, but something bad happened to y. We want to figure out sort of what x is. At least if not too many errors happen, right? That's going to be our goal. So how could I make progress? And maybe you thought and we discussed about this in the exercise class, I'm not sure. Does anyone have an idea? Yeah?
You could use the property or fact, the most bottom fact, because
This thing?
you know that every code word is how do you say it? A product, or no, not a product, but something resulting from that.
Yeah, that's right. So it's like some weird function I can calculate when like plugging in alpha means like doing something with the coefficient alpha and you get 0, right?
Precisely.
Yeah.
And
get,
then
like,
you can
equations.
check where the error is in that, maybe.
Yeah, that's right. So indeed, so we want to think about this condition, we want to use it. So we want to think about plugging stuff into polynomials. So these polynomials need to be our friends here, so that we don't have to say things like x1 plus alpha times x2 plus and so on. We can just say m of alpha. So we want to first of all think of this y also as a polynomial. Okay, so we just think about a new polynomial. Let's call it, I guess, r. Not for remainder, but for received. So let's interpret yn as coefficients of a polynomial r. Okay. So r is y1 plus y2 to the x plus y3 to the x squared and so on, right? The same way as before. So r is y1 with y2x and so on. So we always use the same encoding between strings of symbols and polynomials. Now, I want to study errors, okay? So I know that in general r is not the same as m. M was the message we were trying to send, right? So let me say it differently. So we sent x of n into the channel, but we got y. So if I interpret these strings as polynomials, right? Well, the polynomial corresponding to this one is m, and the polynomial to this one we just call r. So in general, r and m are not the same. And let's make just an ansatz. Let's say, okay, r and m, I can always take the difference, right? And I can call this the error polynomial. Okay. So let's do this. Let's say in general, we can always write r as our original message plus some unknown polynomial e. So now nothing has been learned, right? And now I just gave a new name to the problem. Okay. And so this e, right, is a polynomial whose coefficients are 0 if the thing didn't change and non-zero if it changed. So we have to add a little bit of notation here. And we also give this thing a name. So this equation defines e, right? E is defined such that this holds. R is defined as the polynomial with coefficients y, and m is defined as the polynomial with coefficient x. Okay. And this e we call the error polynomial. Actually, error polynomial. And we can make a general ansatz. We can say, well, this error polynomial, let's suppose that c many errors happen. So c is very unfortunate. It does not stand for code, but it's also count number of errors. Then there's there's c many terms, and each term we can think of, well, suppose a certain place in our string changed. Let's say the ith bit of x, the ith symbol of x changed. So that corresponds into something like x to the, well, I minus 1 actually. So maybe I'll still write this as, let's write this as li. Sorry, L is a better name because more I is our running thing. Let's write it like this. So x of L of I is the monomial that corresponds to position, say, I guess Li plus 1 in this list, right? If Li is 0, then whatever stands in front will belong here, and so on and so forth. So then there should also be a number. Let's call this Ei. Okay. So maybe now it makes more sense. So this thing, right? So this is sort of, if you think of it as a list of coefficients, it's like a bunch of zeros. Then there comes the first power of x, and there's an E1. And there comes, maybe more zeros. Then there comes the next power of x. So if you think of it as a list of coefficients, right? I'll just write it again. E1, 0, E2, and so on. And the location of this E1 is basically, say, L of n plus 1. E2 is sitting at L2 plus 1, and so on and so forth, right? So that's mapping, again, polynomials to coefficients. And you're asking yourself, why do I do this? But let's not task us right now. So this sort of string, everything is 0 except for a few e's. Under our mapping, again, corresponds to such a polynomial of this form, right? Does that make sense? And what we really want to understand is we want to figure out what is C, what is Li, and what is Ei, right? Because that would mean to understand how many errors are there, where do they happen, and what went wrong. Right? So that's what we want to figure out. So let's do this. Maybe I'll make the picture a bit nicer. So some of this, let's say the C is the number of errors. Here I'm actually assuming that this is either all non-zero, right? So in some sense, it's at most C many errors happened, right? Because if an EI is 0, then it's actually nothing changed. These LIs, the exponents, they are the locations of the error. And this location, well, it should be a number in sort of, let's say, 0 up to n minus 1. Okay. And then there's also these EIs, and these are somehow the, I don't know, how did I call this here, like the mistake or the mismatch or something, right? The difference between a coefficient in m and 1 in r. Okay. So if I have so now we have these two error models. We have the Erasure error model and the general one with unknown location. In the Erasure error model, you know the number of errors and you know where they happen, but you don't know these EIs. In this general error model, you don't know any of these three things. Okay. So let's first look at the easier case of Erasure errors. Maybe we can summarize what we just said. So we had these two settings that we discussed. Two settings. Sort of, let's say, Erasure errors. And here only the EI are unknown. And sort of, errors at unknown location, general errors. Unknown. Okay, well, we don't know the location, and in particular, we don't know how many locations of error there are. Let's say nothing known. Nothing. Okay, somewhat globally. So neither EI nor L, nor the Li nor C. Okay. But you could imagine a two-step process where if we have an arbitrary error like this one, we first try to figure out where the errors happened, and then we treat the thing like an erasure error. So that's what we're going to do, and so we're actually we are going to solve the easier case first. So how can I make progress? So what do we know? Well, you said before, what we know is that if we evaluate this message at alpha, alpha squared, and so on, we always get 0. Up to alpha to the t, where t is this redundancy of our code. Now, suppose now we have the sum of these two polynomials, which are the thing we receive. Then we can figure out a relation, right? So we want to learn something about e, right? E is this unknown polynomial, or this partially known polynomial, where I know the number of terms and the exponents, but not the e's. Now, m of alpha 0, r I know because r is exactly what I received as an input as a decoder, right? So now I know that r of alpha is the same as e of alpha. I know that r of alpha squared is the same as e of alpha squared, and so on, because I know that m of any alpha power is 0. Okay. So we know, so this condition, beautiful, this thing implies the following. It implies that, as we just said, e of alpha, and well, what is e of alpha actually? E of alpha is the following thing, I equals 1 up to c, ei, and now I'm plugging in alpha for x. So this alpha to the L1, Li. This thing we know is the same as r of alpha. Again, because the two polynomials on the right add up to that one, and these m of alpha is 0. So that's one equation that we know. And now we have more equations. E alpha to the t, same thing, right? I equals 1 to c, ei. But now I'm plugging alpha to the t. So this is alpha to the t times Li, right? Exponentiating twice, taking the product. So that's another condition, and that's sort of the last of our conditions, right? So we have t of these conditions. Okay. So this is our equation. So these are the e's that we want to learn. There's c unknowns, and we have t equations. Okay, so how many? When can I hope? Only when can I hope to be able to correct for these errors? Well, I need at least as many equations as there's unknown, right? From linear algebra, right? You may know this, right? If you have fewer equations, then there always exist many solutions, and that's bad. But that's good. So we can take if you have many solutions, well, there's only one e, right? Only one error happened. I mean, there's one e that describes the error. So if you have many solutions, we don't know which one is the one that we actually care about. Okay. So you have this beautiful system of equations. Let's call this system 1. And if these exponents are known, right, and c is known, then everything in here is known except for these ei's, and this is really linear, right? This is like applying a matrix to the vector e1, e2 up to ec. Okay, this is a linear combination of the e's, and these r's on the right we do know because they are exactly what we received. Okay, so this we know because r are the coefficients of what we received of our y. So now we have sort of say. T linear equations. So let's say, maybe I should be explicit. If the number of errors and their locations are known, so in the erasure error model, okay, then we can hope to solve this if we have at least as many equations as there's unknowns. So maybe let me write this separately. So sorry for making a mess. So just as a statement of fact, these are T linear equations in C many unknowns. Okay. And the unknowns, well, they're E1, E2 up to EC. They're the coefficients of our error polynomial. But so as a consequence, if we are in this erasure error model, when the only thing that's unknown are these E's, we can just solve these equations. But again, we can only hope to do so if T is larger or equals to C. Okay? Because then we have enough equations. Or at least as many equations unknowns. And that's exactly the condition here, right? We can correct up to T erasures. So it follows from this that for erasure errors, can say hope to correct any number c less equal to t many erasure errors. Okay. Yep.
You say if you have those equations, there will be enough to solve them. But how do you know that these?
No, I very carefully did not say this.
How do you know these equations will be linearly?
That's right. So that's what we are not going to talk about. There would be a bit of number theory involved somehow. One indication I get, it's also related to this n less than q. Maybe what could make you happy is that kind of you could sort of, if you imagine you have these e's, this list of e's, you could sort of imagine this like a Fourier transform of the e's. So such an evaluation, because these are these powers, and you're looking at all these all these powers. So it's kind of like the Fourier transform, and you want to go back. And so the Fourier transform works over these cyclic groups, which are the unit group of fields. But I don't want to give don't want to try giving a forward proof. Okay. But sort of that's the input that one needs. So I don't think. Well, I guess in principle one can. I mean, one could compute that some of the hands-on way would be to try to compute the determinant of the system, and then hope to use that the conditions I impose here are strong enough that things are solvable. But here in this case, because we look at these specific sort of powers of alpha, right? So there's also this Fourier transform interpretation, which is maybe more intuitive. I should say that in Reed-Solomon codes more generally, there's a more general construction where instead of having these parity conditions with alpha squared up to alpha t, one can sort of choose arbitrary points here. And then it becomes a bit more elaborate. And maybe then it reminds you a bit of things like polynomial interpolation, like you're kind of trying to fit, right? Because you could also say this is kind of, you're trying to fit this error polynomial through these points. And I guess over the reals, then somehow when this can be done. But here over the finite fields is a bit more annoying.
Okay, so here they're all going to be different points because alpha is a primitive element.
Yes, and I think now with my choice of t and so on, I think it should be fine. Yeah, exactly. Yeah, that's that's right. Yeah. So I think there was some somehow like because alpha to the q minus 1 is 1. And mod q, so somehow this would be alpha to the n here, which is some of the last position. So now alpha, so basically now, like if you plug in alpha here, then all the numbers alpha up to alpha to the, the location is between 1 and n. Very good. All these numbers will be different if n is less than q. That was it, yeah. I mean, maybe we can talk more about this, maybe even the exercise tomorrow. But so I hope the intuition is clear, sort of, if yeah. So I guess that's why I wrote "can hope," because I didn't want to argue why actually it can be done. Very good. Thanks. Okay, but somehow in practice, right? You could zoom ahead and you could just try to do this, right? So some of the only thing you need a way of solving linear systems. I guess NumPy gives this to you over the complex numbers, sadly not over a finite field. So I'll give you some little like wrap around SymPy, which is this computer algebra package of Python, which can do such things for you, so that you don't have to do it for the homework. But in principle, right, it's okay, I guess, right? You get these coefficients, you just have to evaluate these think of these things as polynomials, you plug in alpha powers and so on, and then you're good. Okay. Well, now, unfortunately, I was hoping to talk a bit more about the general case, if there's no more questions. So the message here is, though, suppose we figure out these guys, the rest can be done. Okay. Good. So now, let's talk a bit more about general errors. So there will be more polynomials coming in and more sort of systems whose sort of solution unique solvability is not a priori clear, but we will push ahead. And we want to somehow see where this T/2 condition comes in. Okay. So what if the errors? What are the locations are unknown? What if locations, in particular, this C is unknown? Let's suppose for a moment actually that we know C, right, to make our life a little bit simpler. So suppose we still know C, but we know neither the E's nor the L's. Okay. So what can we do? Well, what can we do? We define a polynomial. And the polynomial should encode what we are trying to find, but what we don't know. And it's a polynomial that should somehow capture these locations. Okay. And so here it turns out it's something that's useful to do. So let's build a polynomial. It has one term for each location. And the polynomial looks like so. It's 1 minus x is our variable, times alpha to the to the li. So that's the location, the li, and we take alpha to the li away. All right. Good. Now, suppose I knew this polynomial, then I claim I'm kind of happy, because if I knew this polynomial, I could try to find its roots, right? And the roots of the polynomial are the inverse of alpha of alpha li. But if I plug into this polynomial alpha to the minus li, so the inverse of alpha to the l, then this is 0, right? And the zeros of this polynomial are exactly alpha to the minus the location I care about. And I could find those zeros by a clever method, or just by scanning through all values of all values in my finite field fq, from 0 to q minus 1, and I just plug in until I find a root. So I will find a root of this polynomial. Say I will find L of rho equals 0, and then once I have such a row, I'm trying to write it as alpha to the minus li for an li between 1 and n. And that is how I figure out the location. So the goal will be, the logic will be enough to find, to determine L. So if you figure out this polynomial L, then we can find its roots, rho, and then we can determine from each root a location, because the roots are all of the form alpha to the minus li. Okay. So well, this is a polynomial. So as any polynomial, we can expand it into coefficients. The first coefficient, the leading coefficient in here, let's say is 1, right? Because everything else has an x in it. The leading coefficient is 1, while the other ones we have no idea, so let's write them as L1 times x, plus L, what's the degree? The degree is c, so LC times x to the c. Okay. And of course, determining what L is, so that is now what we want to find out. So this is called the locator polynomial. Maybe I should write this down because it encodes the locations. Again, well, of course, finding this polynomial is the same as finding these numbers L1 to LC. So now we have another sort of search problem. Someone want to find these L's. Okay. And the only thing we know, again, is this received message, right? Because we can't find the mismatches. We can't find these E's because we don't know the L's. So nothing that we did here is yet relevant. We have to figure out the allocations. So how can we do this? So there's a nice little trick. So we know that the roots, so the roots, that is the zeros, right? Roots the same as zeros. The roots of L are these alpha to the minus li's. Okay. So I know anything, how much space do I need? Anything like this, L of alpha to the minus li, that's all 0. Like for all I. And so any linear combination I'm going to write down is still 0. And I want to write down a linear combination that somehow contains, well, it will always contain these L's because there's an L here, but that somehow also contains, say, R. So let's try to do this. So let's actually take something that looks as follows. So this is EI, the ith coefficient over here, which we don't know, right? We don't know this thing, but mathematically I don't care. I can just go ahead. And here I'm going to take alpha. Oh no, does this fit? Sorry, let me just close that. Let me write LK J plus C. Okay. So J is something new we haven't seen yet. And now I'm writing what I wrote before, alpha to the minus L. There's no K, that's I. Let's say J, oh god. I is L on my thing and L is K, and I don't know what went wrong in my life. Okay. So this J is a new thing, okay? This J is a new thing that I just want to fix for now. Hopefully all the other symbols make sense. So EI, enough colors, everything will make sense. These are the coefficients that we know, and these locations that we wish to understand are these L's. Okay. And again, the logic is, if I plug in alpha into L, I get 0, so any like junk that in front also leaves this thing 0. Just C, okay. So we have this thing. So now I want to rewrite this, okay? I want to somehow expand this. So I would like to write this as actually in terms of this error polynomial E. So how could I do this? Okay. So I mean L is this beautiful locator polynomial, that's a bit strange. But L I can expand term by term. Okay. So suppose I throw everything away except for the constant part. What have I then written down? Okay, so if I throw everything away except for the constant part, well, this is just 1, right? So this goes away. But what I wrote here, what is this in terms of what's written on the right? Well, this is just the error polynomial, not evaluated at x, but evaluated at alpha to the x plus j plus c. Does that make sense? So I claim that, so there's more terms coming, sadly. But I want to say there's something like this at the beginning, which should be the same as what I wrote here. Does that make sense? I mean, I can't look because I have to hold this paper, so you have to check whether what I wrote here. I guess what I wrote here is the same as this, if you plug it into the definition of E on the right. Does that make sense? Okay. Very good. Now what happens with the next term, with this L1 term? Okay, now I continue. I'm writing L1 times, and now, well, I'm looking at the same expression, except that now there's an x here, and the x becomes alpha to the minus Li. So what should go here? So what is the power of E? What do I have to plug into my error polynomial to make this work, right? So what I want to calculate is this sum multiplied by, well, x substituted for alpha to the minus Li. So basically this, right? So I have a minus 1 in here, right? That's what I'm going to get. So this should hopefully be alpha j plus c minus 1. And so on and so forth, okay? So at the end I get LC e of alpha to the j. Alpha to the j, right? Because in the end I have, well, LC is LC. X to the c is alpha to the minus c times Li. The minus c times Li cancels the plus e to Li times c over here. So only j remains. Good. Now again, I'm much more happy than I was before, and I wish to ask you why. Again, our goal is to determine this LC. Why is now life much better than 2 minutes ago? Oh, sadly it's because of what I raised here, right? Oh yeah, go ahead. Yep.
So the error functions in the powers of alpha are exactly the received polynomial evaluated in alpha.
That's exactly right, and that's what you say is true as long as this exponent is at most t, right? Sure. And that's exactly right. So I'm going to write now. So and that's one aspect, right? Sorry, were you saying something or okay? So that's one aspect. So we actually know these guys because they're the same as the R of alpha j plus c and so on. As long as this exponent j plus c is less or equal to t, right? That was the magic parity condition. Or this magic condition. And the other thing is that, again, this is a linear equation. There's a linear constraint on these L's. And now maybe it's clear why I have this J floating around, because everything we said is true whatever J is. So we can vary J, and we get many conditions. Okay, so J is still not fixed yet. And, well, we would like to determine C of these coefficients, right? Oh, no, we should stop, right? Good. We continue. But we're almost done. You'll be most happy in 1 second. So we have this linear equation, right, in C unknown. So we want to determine C things. So I know I need to take at least C of those equations. So what I could do is I could just let J run from, I guess, 0, I suppose, to C minus 1, for example. Or, well, I guess I want to start from J equals 1 because I set up things by that way. Sorry, we know E of alpha up to E of alpha to the t. So I should start with J equals 1, I think. Let's see if it works out. Okay. So I'm going to write down another system of equation like the one over here, or maybe in matrix form even. And so I'm already using what you said, right? So if this is the constant part, right? So that's going to be on the right-hand side of our system of equations. So I want to write this as like some, some matrix times a vector, and the vector in our case is L1 up to LC. Okay, maybe we can compress this so that there's actually space left. L1 up to LC. But these are my variables, okay? And then on the right hand side, I want to write, well, minus this thing, right? So say minus E of, let's try with j equals 1, right? So if I write this down for j equals 1, then this would be alpha to the c plus 1, and so on. Okay, and then that will be the last term. And similarly, this row here would be, well, E of alpha to the c, right? That's if j is 1, and so on up to E of alpha. Formatting is not great. Does this make sense? So if I write this down, right, it's like L1 times E of alpha to the c, up to LC times E of alpha equals minus E of alpha of c plus 1. And this is this equation for j equals 1. And now I'm just repeating this. For higher j, right, I'll get higher powers of c. So I guess the bottom left thing should be, apparently, alpha to the 2c minus 1. Yeah, I think that's right, yeah. Yeah, alpha to the 2c minus 1. Okay. All right, up to E of alpha to the c, I think. Yep. And then on the right hand side, we have E of, let's see, I guess 2c here. Yeah. So again, this is sort of corresponding to j equals c. Cool. And now we say exactly what you said, right? I mean, is this okay? Like, did I plug in things correctly? So the last thing should correspond to j equals c, right? So L1 times alpha of 2c minus 1 up to alpha to the c, and this one is the one where here c plus c is alpha times 2c. So that's our equation. It's a quadratic system. We, for now, pray that it has a unique solution. Well, now we use what you said, right? Because if 2c, right, that's the largest exponent. If 2c is less or equal to t, then we can replace e by r, right? Because we know that e of alpha equals r of alpha, and so on, up to e of alpha to the t equals r of alpha to the t. Okay. So now we can fix this, right? We can sort of change what I wrote, and we can replace this by r. Well, R. And that's brilliant because now we know everything. Okay. So this system I want to call system 2. And we could hope to solve this, right? And so hopefully, again, if the number theory works out right, then if C is the right number of errors, where all these EIs say are non-zero, then we can solve the system and determine L. Again, once we have L, we by definition know this locator polynomial. We can determine its roots, we can determine from the roots the positions. So we're good. Okay, we should really stop, so maybe in the breaks you can think about what should we do about C, and the answer will be a bit disappointing. But you can still think about it. Okay. Good. Let's have a break until 5 past. So I guess the punchline of just before a break was that if we don't know the location, we can build this fancy locator polynomial. A priori, it's again an object that we don't know. But if we knew, in particular, if we knew its roots, then we would be happy because the roots are just encoding these locations. The roots are alpha to the minus the locations. So we want to find the locator polynomial. We expand it in these terms of these coefficients, L1 to LC. Then we we use the fact that this alpha to the minus the positions are zeros of L. We can build some crazy linear combination, and this crazy linear combination is built in such a way that one can rewrite this whole thing as some evaluations of the error polynomial at various points, at various powers of alpha, with these coefficients L1 to LC mixed in. And now somehow, again, the error polynomial is something I don't know, but I know that if I plug in powers of alpha, it's the same as this R polynomial. And R polynomial I do know, it's just one representation of these Y's, of the message that came in, of the corrupted message that came in. So I can actually compute all these things, provided the power of alpha is not too large. And the largest power of alpha that appears in the system is 2c. So if 2c is less or equal to t, then I know all the numbers in here, and I can replace E by R everywhere. And so I get this linear system that I call 2. So that's a system of C equations and C unknowns, R1 to LC. And provided I can solve this, then I can figure out these locations. Okay. And it's nice, the condition that we get here is exactly what I claimed. Right? The condition we get here is that the number of errors that we can have, C, is at most T over 2. That's what we claimed at the very beginning. I think it's no longer on the board. Now, how do we find C? Well, we don't really know. So what people do is they would just try. They would start with the largest possible C. And then if this system of equations has determinant 1, has non-zero determinant, so if it has a unique solution, then that's what we're going for. Okay. And if it has not a unique solution, if the determinant is 0, we reduce C, we continue, and so on and so forth. So that's sort of what one does. So we maybe to conclude, and so one should say much more things like why is this a good procedure, why does it always work, and so on. But I think I want to skip over this because maybe this is sort of peak mathematics for today. So we still don't know C, but I can point you also to places to read about these things in more detail. So we don't know C, so we will just try from say starting at T over 2. Down to 1 until the determinant of the system, I'll just write determinant is non-zero. Okay. So determinant of this matrix, which means the matrix has a solution and has a unique solution. The system has a unique solution. Again, because somehow if we had multiple solutions, there would be something inconsistent, right, about these locations and so on. Okay. Right, for example, like one way to have multiple solutions is kind of like, if this coefficient is 0, then many else will do, and so that's kind of why you will have a non-unique solution if you choose C to be too high. Because somehow there's no problem of increasing C here if these E's don't have to be 0, but then you just don't learn anything new. At any rate, so that concludes now, and now I can write down a more formal algorithm for the decoding with certain errors in sort of pseudocode. You'll do this tomorrow with Fake. But basically that's what's going on. Step 0 is computing all these R of alphas. Let's say step 0 is, you compute actually R of alpha up to R of alpha to the T. If there's no error polynomial, then these should be 0, right? If one of these things is non-zero, then an error must have happened, right? Because we know this is always e to the alpha. So if there's no error, the e polynomial is 0, so this would be 0. So we compute this thing. If any of these objects, R of alpha up to R of alpha to T is non-zero, we must have had an error. Then we're trying various values of C from the maximum number of errors down to 1. We check when can we solve this uniquely. If we can, then we learn these coefficients L. We get the locator polynomial, which is that we now managed to actually learn C as well as these LIs, and now we solve this system to figure out the E's, these mismatches. Okay, so once this part is done, we're in the situation of erasure errors. It's just like that to get there, we had to actually have that 2C is less or equal to T. All right, maybe just to clean this up. So this is DC, so we just try it. So that's the pressing thing. Good. Maybe we can do an example, and then we completely switch gears. I guess my example was here on the. Maybe we'll just do an example for erasure errors. Let's see, we have the erasure errors. Very good. So let's try if we can make this work. So we are again in this situation, right? So here we discussed k equals n, we code 1 into 3, mod 5, the generator is 2. And in particular, we learned that if you want to encode an arbitrary symbol s, right? K is 1, so we are encoding single symbols at a time. We get this beautiful encoding into 3 symbols, where I made this green, right, because that always had to be the same as this one. The last K symbols had to be the same as the source message. And now we want to start an arrow. So imagine yn that we get is one where, say, let me see what I did here, where these two things got erased. Okay, so it's imagine instead of, maybe I'll write it like this. Well, if it was like so, no error would have happened, right? But imagine that these things got erased. Okay. Well, actually, let me write x here. So x is what I wrote, and now we imagine these two spots got erased. We have no idea what they are, or maybe something. Maybe this one is 3 and this one is 1 or whatever, or both are 0. But we know where these errors happen. So suppose. So imagine that's what it started from. These guys got erased, and so what comes in to our machine is, for example, into our decoder is, for example, 0 minus S0. That could be one way of modeling it, right? So I put zeros here, but I know where they happen. So now there's two objects that we have to deal with, okay? So there's two polynomials of relevance. Well, the initial polynomial, I guess, that we never wrote down is the one corresponding to this message here. And now there's the polynomial R. What is R in our situation? So what is the polynomial R? Minus Sx, exactly. Because I'm just taking these numbers, right, 0 minus S0, and putting them in front of, 1x, x squared. So it's like 0 plus minus S times x plus 0 times x squared. So this is R. That's the polynomial that just describes what came here. Right, and it doesn't really matter what I put here, right? So here I model this erasure error as placing a 0 on both spots and telling you the error happened here and here. But since somehow we don't know what this was, we can put whatever we want here. Okay. Let's put 0 here to make the polynomial. What do we know about E? Okay, so what is the ansatz that we should make for the error polynomial E? We know the locations and we know how many errors happened. We know 2 errors happened and they happened at location, as I can say 1 and 3. I guess if we index things by 0, oh my. No, I guess it's okay, but it's not what I wished for. It's tragic. It's just tragic. I think that I wrote this wrong here, right? I should have written 0. I should have written 0 to n minus 1, or written minus 1 here, right? Do you agree with this? Yeah, it's kind of a pain. Like, I mean, of course it doesn't matter at all, but I guess the way we wrote down things here, right, is because x to the 0 corresponds to spot 1. Somehow these exponents should run from 0 to n minus 1. Sorry about that. I should also say this in a second. Okay, so we follow this convention. What is then the ansatz for this error polynomial that I should make? What is a polynomial with some arbitrary coefficients that models going from our original code word to this one? Again, we're trying to figure out what these places were, so we don't know it yet, right? So these are unknown coefficients. But what's the polynomial look like? Well, we have one error at location, I guess 0 in this convention, and another at location 2. Right? So this polynomial I can write as, I guess, e1 plus e2 times x squared. Does that make sense? So I know there's 2 errors, so there's 2 terms in this polynomial. And I know that one error happened, so to say, at location 0. That is what influenced this part. That's because I know here is an error. And also know here's an error that corresponds to x squared, right? When I map coefficients to polynomials. Is that clear? Please to ask if not. So what I'm saying is, if you think of this as a polynomial, right? This is the polynomial minus 2s minus sx plus sx squared. It's this one, right? That's our message polynomial m. Right? I'm just writing this down as a polynomial. The thing we received r is just minus s times x. These two things differ in something, a constant part plus a quadratic part. Okay? And I know this because, bless you, I know this because I know in this erasure error model, I told you the errors happen there. So you know you can go from R to S just by modifying these two spots, and that corresponds to arbitrary E1, arbitrary E2 there. Is that, am I saying it wrong? I see unhappiness. I don't like it. Okay, so okay, so we receive a bit string. We know that the bit string differs here and here, plausibly, possibly from xn. Here it actually does, unless s is 0. We want to fix this, but we know because the errors happen here, we can fix it by sort of an error string that is, has a 0 here, but some E1 here and one E2 here. Okay, and I encode this as a polynomial like so. Okay, so now we can proceed, right? And now we can. What was the next step? Well, for erasure errors, we knew that we just have to look at these linear equations. Okay, and what are the linear equations? Well, we want to look at two linear equations because we have two errors here. Right? We want to figure out, so we have to figure out these coefficients E1 and E2. E1 and E2. So our system is going to be, well, E of alpha should be the same as R of alpha, and E of alpha squared should be the same as R of alpha squared, right? So these are the two equations that we have. And from those we want to figure out E1 and E2. So we know alpha, right? We know an ansatz for E, and we know R of alpha, right? Because that's R. That's what we receive. So let's write the system sort of concretely. So what is alpha for us? Alpha is 2, right? So the first thing will be E1 plus E2 times 2 squared. Right? That's our E of alpha. And that should be equal to R of alpha. But R of alpha is minus S times alpha. Okay, does this make sense? Let's see if it makes sense. Looks like so. Well, and here, the second equation, now we plug in alpha squared. So it's E2, and now we plug in alpha squared for x. So we get actually alpha to the 4. So alpha is 2. Alpha is 2. Alpha squared is 4. Then what is alpha to the 4? Well, it's 16, but 16 is 1, not 5. Another way of saying it, this is actually minus 1, not 5. Minus 1 times minus 1 is plus 1. Okay, so alpha to the 4 is 1. So 2 to the 4 is 1, not 5. So that's just a 1 here. And this 2 to the 2 I could just as well write as 4, right? So that's the extent. Or maybe as minus 1, which is even nicer. Okay, what do I do here? Again, on the right hand side, I want to write on R of alpha squared. Alpha squared is minus 1. So minus 1 times minus S should be just plus S. Let's see if this works. Aha, yes, and we wrote alpha, but alpha is 2, so it's minus 2S. Phew, okay. So now we plugged in everything. We plugged in our choice of alpha, our choice generator, that just depends on the code. We plugged this into this ansatz for the error polynomial, so this is some linear expression in E1 and E2. And on the right hand side, well, we plugged in R of alpha and R of alpha squared, where R is this polynomial corresponding to our corrupted message. So now we have a nice system, and this is the system that I called 1. And now the only thing I have to do to fix the error is I have to determine E1 and E2. So what is E1 and what is E2? Any guesses? So how can I solve the system, right? I mean, I guess I could add the two equations and then I get 2E1 equals minus 2S plus S minus S. Also, how can I solve this? It's a bit annoying. I have to solve this modulo 5, right? So which E1 satisfies this? Okay. So 2 times which number is 1? What's the inverse of 2 modulo 5? 3, exactly. 3 times 2 is 6, is 1, not 5. So if I multiply this equation through by 3, right, I get E1 on the left, 6E1, but it's E1 on the left, and minus 3S on the right. Minus 3S is the same as 2S, because minus 3 is the same as 2 mod 5. So now we have E1 is 2S, hopefully. And then I guess E2 should be minus S for this to make work. E2 should be minus S, again because of this equation. Okay. Phew, so this is E1, E1 is 2S, and E2 is minus S. Let's see if this makes sense. What is now the error polynomial? I just plug it in. So now we learned, right? E is E1 plus E2 times x squared. E1 is 2S. Plus, well, minus S times x squared. Okay. So now R equals M plus E. So M is R minus E. So what is this? R is minus Sx. So I guess we have, because we subtract E, we have minus 2S, and the minus Sx from here. And now minus times minus plus Sx squared. Okay. And now we are relieved, hopefully, because now we have, we think this should be the message that was being sent, and its coefficients are minus 2S, minus S, and plus S. So if we translate this back into a bit string, xn, well, the first coefficient is minus 2S, the second one is minus S, and the last one is plus S. Okay. And that's hopefully exactly what we wrote here, right? That's our correct code word. And we corrected both of these erasure errors. Right. So this maybe should be green, because the last thing is always our source message. So now we're done, right? We can just read off, this was the message. It's always in the last spot. Phew. So that was the easy version with erasure errors. The hard one maybe you'll do tomorrow. It's also in lecture notes, but I think it's nice to just do it once. I think I would like you to be able to do this for like small Q, like here, to do this decoding of erasure errors, but certainly not the general errors. On the homework, you may want to program the general errors if you like. But again, there's an algorithm that we will discuss tomorrow. Any questions about Reed-Solomon code? So that was just an introduction to the sort of world of algebraic codes. So that's a bit fancy with modulo Q and all these things. But it's kind of nice. Like it's sort of everything that seems pleasant and one uses the tricks of polynomials in linear systems. Any, did you wanna? No, you're scratching.
Well,
yeah.
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 Do you have to be able to encode stuff? Because calculating the remainder modulo some polynomial is not fun.
No, it's actually very easy. Actually, it's like long division in a way.
Yeah, it's not fun.
I mean, you mean for you?
Yes.
To do it like in homework or even work.
I don't like it.
You don't like it?
I don't like to do that on the test.
Well, I can understand that, but I can't see a solution. I would hope that somehow it's a, so if there was a single symbol like here, I guess it's not so hard to do this division with remainder, because you always know the answer will be S times G. So maybe, if you have two symbols, then maybe there may be many steps, and maybe several intermediate steps. But somehow if things are low degree, somehow it should maybe not be so terrible. I would hope. Maybe it's a good thing. Maybe you can ask Fig tomorrow to give you some more polynomial division problems to practice. And if it's still really hard next week, let me know. We can discuss more. Maybe we can do a Tuesday polynomial division practice. Just give it a try, and if it really seems terrible, then we can talk more. But if the degree is 3, then I guess it terminates after at most two steps or so. I guess it's keeping track of minus and plus signs, a bit annoying. Modulo Q, one has to keep in mind. But I hope that's nice. Okay. More questions, critiques, suggestions for the test? Okay. So then that's one topic. I guess now I want to give a real introduction to something that's completely different, so it's more like pastime and fun. I guess the point here was like there is these nice algebraic codes, but then there's many other codes like LDPC codes and turbo codes, where there's no nice algebraic decoding procedures that can just run sort of exactly like we did here. So there one uses more algorithmic solutions, and they're sort of based on, I mean, the motivation in the end is where we have the sort of decoding problem, and last time we explained what we really have to do is we have to find the S that maximizes, you know, this posterior for a given received string yn. And yeah, usually, I mean, basically what we have to somehow calculate such probabilities. Usually they decompose in some way. There's some like, you know, this S maybe has some IID thing in it, and Y, like the channel factorizes because it's memoryless. And so there's like some structure, and also your error correcting codes usually have some sort of graphical structure, and then things like graphical models come in, if that tells you something. And so somehow we have graphs, so we have to solve problems, global problems about, you know, computing probabilities in some hopefully local iterative fashion. And so there's heuristic algorithms, sometimes I guess called message passing algorithms, or the Min-Sum algorithm, Viterbi algorithm. Maybe these are, I'm not sure if these are things some of you have heard. So I want to give an introduction to this with something that has nothing to do with coding, and then I think next week they will apply this to a coding problem. That's the Tuesday lecture. If he's still up for it, even though I may not finish everything I was planning to do today. Oh, I guess there was a typo before. I think in my decoding algorithm, someone pointed out I may have left out the x to the t here. If I did, then you probably fix this yourself. Another thing that's maybe fun to mention since we anyway started here. So what's curious about these Reed-Solomon codes is they have this very large alphabet, right? So each symbol, right, could, for example, each symbol, I don't know, in the source message, for example, and also in the code words, corresponds to like one out of q many different values. So if q is large, so if you think about, I mean, in practice we often communicate digitally in bits. So each symbol and each code symbol corresponds to many bits, log q many bits in general. Which kind of means that in some sense, if one of these s's change, that can correspond to many bit flips, right? Many bit flips, if they're somehow local, they will only change a few of these s's. Right? So what I mean is the following: suppose if a source measures like this, or let's say a code word, x1, x2, and then up to xn, and say q is, you know, say 929, like for this barcode, then this q, right, would actually correspond to many bits. I have no idea what log q, well, I guess I do, it's like 10 bits if you round up. So actually there's 10 bits for each symbol, okay? So that, I don't know, it's like, whatever, 10 bits. And then another, you know, 10 bits, and so on and so forth. And now imagine that, you know, someone scratches your barcode, right? And they mess up sort of a stripe like this, and it's all gone. This only impacts 2 symbols of your code word. So in some sense, these codes are kind of good against, I think sometimes it's called burst errors or something like this. Like, I don't know, someone like locally, I don't know, hits your hard disk. Well, I guess it's not a good idea to hit your hard disk, but in general, also they don't exist anymore. So these sort of physically localized errors that happen often, or I guess one example is sort of a weak cell phone signal as you drive through it, under a bridge or something like this, right? And signal peaks briefly. It's like noise, and then it gets better again. So that's useful. Okay. So these Reed-Solomon codes are used indeed on like sort of on the low level of sort of your hard, like inside your hard disk. So that the hard disk controller does, for example, used to do Reed-Solomon encoding. Or some kind of satellite communication codes are usually combinations of Reed-Solomon and other things that maybe we'll briefly discuss. Okay, so now we switch gears though when we talk about message passing algorithms. The CS people among you, they will recognize this maybe like this closely related to dynamic programming in a way, which is maybe not really about programming, but a kind of an algorithmic design technique. And so, but the general logic is somehow we have like some situation, and there's some like geometric structure, there's a notion of neighbors and so on, and we want to solve a global problem by talking locally, by sending messages to our neighbors. And there's this like a beautiful but silly example of counting, right? Suppose you have a bunch of people in a line. So many people in a line. Actually, for all of them. They lose their head because it's late and they have to do information theory. And so they are standing in a line, it's a really long line. They have no idea how many they are, but they want to figure out how many they are. Okay, so they can talk to their two neighbors, or the people in front or in the back of them, so both ways. And of course, if I'm standing in the back of this line, I know I'm the last person. The person in front knows there's no one in front of them. Like they have appropriately spaced so that they can talk and see each other. So how could they figure out how many they are? Right? So that's kind of what we call this decentralized counting. Okay. What's a good strategy that these people could pursue to figure out how many they are? Right, this is actually one of this control freak sitting here. He's really curious about who's in the line. He likes lines. He likes counting. Yeah.
If it gets to the end, the guy says 1 and the next guy says 2 until it's at the end, and then just get shouted back or something.
Sounds right. So we start. This guy says 1, and sort of whenever this guy hears a number, he adds himself and he moves it forward. Right? So 2, 3, 4, 5, say, and sorry. Good. Everything else is good. Okay. And this guy could behave the same way, right? This person could also say 1, show it back, and then this one goes down 2, 3, 4, 5. And now there's the happy situation that somehow these messages are actually meaning, right? Because if I sort of suppose we focus on this person, then what's the meaning of the message that comes in here? Well, it says that there's 2 people behind them, and the message that comes here is that there's 3 people in front of them. So they would know the total number is 3 plus 2 plus themselves, right? Because they didn't count themselves yet. So 3 is before, 2 behind, 6, and so correct. So that's nice. So that's the simplest kind of message passing algorithm that solves this problem pleasantly. You could ask, does it generalize to other graphs? It turns out it works for arbitrary trees. So trees are graphs without cycles. And the reason is that basically this problem here, as well as for tree, sort of it decomposes into smaller subproblems, right? So the global problem of counting decomposes into counting in front, counting behind me, plus myself. So also in a tree, right? In a tree, somehow, if you have a tree, so here's some graph, and it has like some components. A tree has the property, so suppose this is a vertex. A tree has the property that if you remove a vertex, like stuff becomes disconnected in a way, right? There's no other way to connect these things. So somehow counting in a tree is like from a perspective of a local node is like counting here, 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 and adding themselves. And then we do a similar algorithm. Maybe you can also do this tomorrow. Now we do a more fun problem that's a bit more probabilistic in the end, and I mean counting may be more harder. I mean here counting by looking was not so hard. Okay, so let's look at a situation where counting even by staring at small examples is annoying. So this is decentralized counting. And let's count paths in a grid. Okay, so for some reason we have say a grid. We have sort of a part of Manhattan, I guess. So we have a rectangular sort of street system, like so. And I have a starting point A, I have an end point B, and all moves that I want to make are to the right and to the bottom. I will never move to the left or upstairs. Okay. So particularly no path will have a cycle. So paths go to right, combinations of go to the right and go down. Okay. And these are the nodes on this graph. And now my question is, well, I have 3 questions for you for the remaining, I don't know, 3 times 2 minutes or so. First question is, what's the total number of paths from A to B? Second question is, what is the probability that a random path goes through a certain point P? Okay, so imagine I have some other point floating around P, and I would like to know sort of what's the probability that a path goes through P or equivalently, how many paths go through P, to a fixed P, right? Because if I sample uniform at random, the probability of a path going through P is then just the number of paths going through P divided by the total number of paths. So what is the number of paths from A via P to B? Okay. For any P, you give me P, or I give you P, you have to count. And the last question would be how to sample such a path uniformly at random. How to sample path uniformly at random. So maybe we can still solve this today. Again, yeah. So maybe we can talk about this and think about how this message passing idea might work. Just for concreteness, just for clarity, you could imagine trying to draw a path at random just by starting at A. Well, I guess here we can only move to the right, so that's not so hard. Now you could say, oh, the probability 1/2, I'll take this route or this route, and so on and so forth. That does not give you a uniform distribution. Because it could be that more paths have to go this way than this way. I mean, maybe for this junction it works, but for other junctions it will not work. For example, for this one it will not be true that this and this is equally likely. That turns out to be the case. I guess one way of seeing it is that set up with these decisions here, you always make choice with probability 1/2. So all the probabilities in the game should be powers of 2, but they're not. Like the number of paths doesn't need to be power of 2. So that's one sort of indirect argument. But maybe just to keep in mind. But we can start with problem 1. So how could I solve problem 1? So how? Yeah.
You follow a path and every corner or every cross that you split, and you write down at each path how many possible paths can be taken to there.
Mm-hmm.
And at each crossroad you add the amount of inputs together, and at each output you write it down as well.
Yeah. Okay. Very good. So you want to? I mean, so that's sort of. That you already described sort of taking a certain order through the game. I'll try to say what you said in slightly different terms, just focusing on one node at a time. And I imagine these are all like people on the grid, and they can hear, and they have like incoming messages from from the left and from the top, and they shout things in the other direction, right? That's kind of what you proposed, I think. So then indeed we would start by A, and A would shout 1 because there's only one path from A to A. Right? So let's say, and let's call this the forward algorithm. Forward pass. The forward algorithm would say node A, so that's sends 1, and I'll use the word downstream. So downstream means sort of to the right and to the bottom. So maybe you can imagine there's like directions. So that's sort of forward. So the directions indicate in which direction we are allowed to move. Paths are allowed to move. Okay. And so node A just says always 1. Okay. Now in all other nodes, at any other node P, what you were saying is, well, we have to see what comes in, right? Because then we know the number of paths that arrive at P, from A to this point P, wherever P is. Maybe it's here, like here there's only 1, here there may be many, right? And so that's the number of paths that go to P via here. Then the message from here will be the number of paths that come to P via here. So if we add them, we get the total number of paths that go to P. And then this message we send here and here. So we wait, so that the logic will be wait for messages from, I don't know, upstream, I guess. So 2 in general, right? 1 from here, 1 from here. And we just send the sum of these 2 messages, right? Here and here, downstream. Okay, and so the picture that you can have in mind, let's just focus on one node P. Somewhere there is A, right? Then there's sort of these 2 predecessors, these 2 upstream neighbors, like, so let's say X and Y, right? And then there's somehow paths that go by X, there's paths that go by Y, and the crucial property is the number of paths from A to P, as the the number of paths from A to X plus the number of paths from A to Y. Right? Because any path from A to P has to go Y here or here. So once you know this, right, and there's a plus sign, that's why there's the sum over here. Maybe I can try to do this. Let's see. So here there's one incoming guy, one, and nothing I have to add. So we send one down. Here comes one in, one down, one. Well, here's only one coming in, so one goes down. Same here, one. So now it's more interesting. Like one, there's. If you look at this node, well, we know there's one path like so, another like so, and we need 1 plus 1 is 2. So we're sending 2 downstream. Now we have 1 and 2 coming in, so we send 3 and 3. This 2 is just the same as here. Now 2 and 3 is 5, and 3 and 1 is 4. So now at node B, well, we 4 and 5 arrive, so in total there's 9 paths in the picture. Okay. So pleasant. So 5 and 4. I guess I should have written down the algorithm slightly nicer. So in the end, the sum is 9. There's 9 paths in total. There's also another way of doing it, right? So really what this algorithm does it, right? At each node, we are actually computing how many paths there are from A to P. Right? That's really what's going on. So there's more information, not just the total number of paths, because this will be, if we are at node P, this will be the number of paths from A to P. So this is the forward algorithm. And you could, in the same way, have a backward algorithm that starts at B and that goes back. And that, we just replace upstream by downstream. So we are waiting from, so this guy would wait from a message from B, this one would wait from a message from B, so it would be 1, 1, and so on and so forth. And then what we would be computing is the number of paths from P to B. So that's the backward algo. So this one starts with node B, sends a 1 upstream. And okay, I don't maybe have to write it down. We wait for messages from downstream. We send the sum upstream. And the sum now computes something different. That's a crucial point. We learn actually more stuff now. The sum computes now number of paths from P to B. Okay. Does that make sense? So now we can also solve problem 2, because actually the number of paths through P is the number of paths from A to P times the number of paths from P to B. That also factorizes. I guess it was very confusing to put this into a bubble, but yeah. So problem 2 was then counting the number of these paths, but the number of paths from A to via P to B is, as we were just saying, the number of A to P times the number from P to B. So if you do both a forward and a backward pass, we can also solve this problem. Okay, so you run the algorithm one direction and the other direction, and you actually remember at each node what you sent in the 2 directions. Then you know this number, you know this number, you can compute this one, and now you could even sample, right? You could sort of sample as you wish. So you could draw, you could compute, for example, what's the probability of going through a certain P and so on. So now how do we actually sample in setup 3? So in question 3 was the problem, I want to find a random path, okay? So how should I go about this? A uniformly random path. Does anyone have an idea how these 2 algorithms, the forward and the backward one, can help? Yeah.
You could, since you know how many paths come into the node, you could use that to determine the probability of taking that path. Because you don't want 50-50, for instance, because then the paths with a lot of incoming nodes will get favored over paths with less incoming nodes. So you could scale it to the amount of incoming nodes, and then you will get a uniformly random distribution.
That's exactly right. So suppose we start here, right? We start at the back, for example, and we know there's 5 paths that have to come in here and 4 over here. Then we'll somehow throw an unfair coin, which which says this path with probability 5 over 9 and this one with probability 4 over 9. And then we would take one of the two routes. And now, for example, suppose I flip my coin and this was the outcome. Now I'm here. Now I do 2/5 versus 3/5, and so on. So it's exactly what you described. So somehow you do first the forward pass and then you build your path backwards according to these probabilities, or you do the backward pass first and you build your path forwards. That's right. So I can maybe say, I guess since we did the picture here, you could, let's say you run the forward pass and then you build path starting from B, right? So B, and somehow you would select somehow a node in the path. I don't know, sort of PL, let's say, according to, let's say, P of. Oh man, I guess I need a picture. All right. So suppose I'm at P right now, right? If I'm at P, I want to select the X or Y. So in this situation, in situation star, you would select X with which probability? I guess the probability, well, the number of paths, say, from A to X, divided by the number of paths from A to P. That's somehow the same thing. So, and likewise Y, right? Because these two things add up to the probability that's normalized. So that's the probability we choose X, and similarly, you will select Y with probability. That's all. Good. I think that's all for today. There's another example that one could have done, which is finding a shortest path in a graph. There you can do a similar thing. You combine the steps differently. Like there at each step, like you're trying to, even if you're trying to find the shortest path, then you would sort of say, at each node somehow, the shortest way to get there is the shortest way of getting there plus this cost. Or if that one is shorter, the shortest way to get here plus the cost of this edge. So it's like a minimum of two options. Instead of summing, you would take the minimum of two things. That's called a min-sum algorithm, because you minimize and then you sum stuff. Okay. So that was kind of basically the last thing. And I guess that's all.